You start off 0 dimension, 1 dimension, right? That's 1 dimension. So how do you create a 2-dimensional line? Aha. You go orthogonal, and you slide the line orthogonal to itself, right? You slide it, literally. So what you do is you take this line and you slide it down. Literally, you slide it down until you travel a distance equal to the line, and then you get into 2 dimensions, right? You slide it, and then you stop here. And this equals that. Now, remember, the sliding itself is part of the interior of the square. This is crucial, what I'm saying now, right? So the sliding itself is part of the interior of the square. I'll call it 2D squared. Okay, now we do the same idea. We use the same idea. We're going to slide this square along another axis orthogonal to both sides. Okay, so we slide that. Okay, so now we're going to be doing this. We're going to take this, here's another axis. We're going to imagine this axis orthogonal to both sides. And we're going to take this square and slide it along a distance equal to the sides. And then stop. But remember that as I'm sliding that square along that third axis, right, the sliding itself becomes part of the interior of the new square in 3 dimensions, something we call a cube, right? The sliding becomes part of the interior. Get it? Everybody's got that? Okay. All right. So we do that, right? So we slide this along. Let's use blue and yellow. Oh, there it goes. That's that corner there. It's a dangerous corner. All right. So I'm going to make another square here. Sort of looks like the first one. This is the final square, right? And then the sliding occurs here on these blue lines, right? So you slide along here. Okay? All of a sudden, what you've done is you've taken this square and you slid it along an axis that's orthogonal to the original 2. And the sliding itself is part of the thing that we call the cube. The interior, the surface, the edges, the faces, the cube. Now, it gets interesting. See, now a mathematician says, big deal. So I can't see the 4th axis, so I'm just going to make a line. I'm going to use the same principles. Exactly the same principles. Okay? So what we're going to do now, it's going to be a little hard to visualize, but I probably can do an interesting job of it. We're going to take a 4th axis. Here it is. Now I declare, once and for all, that this 4th axis is orthogonal to the other 3. Okay, I declare it, because I can't see it. None of us can, well, not that I know. Maybe some of you are aliens. Maybe you can see it, but I can't, right? Okay, so what we're going to do now is we're going to take this cube and we're going to slide it along the 4th axis. An equal distance, a distance equal to the distance of or to the length of one of the edges. Which means that when I'm doing the sliding, everything that you see, no matter how crazy looking it is going to be part of the hypercube. That's the hard part. We can't imagine that because we can't see. Okay, so let's do it. Now, it's not that bad. I mean, it looks bad. So I've got yellow, blue. Maybe I should make this blue. So make this blue. Okay, so my new sliding rule is going to be yellow. So okay, how many things do I slide? Here's 1, 2, 3, 4, 5, 6, 7, and it should be 8. Did I just 1, 2, 3, 4, 5, 6? Ah, here it is, 8. Right? So from each one of these points emanates a line. So we do it. Okay, so here's the first one. And it goes up to here. That's more or less the same. Well, more or less. Okay, like that. Then I do the same thing here, right? And do the same thing here. More or less. I'm going to do the same thing here. The same thing here. The same thing here. 1, 2, 3, 4, 5, 6. I'm missing 2. This one here. And which one? This one here. Okay, you see what I'm doing now? I am now sliding that cube along a fourth axis that I can't see. But I'm doing the sliding anyways, because I'm a mathematician. And we can do this stuff, right? Okay? And now, once you've done, if I've done these things correctly, if I did the sliding, the measurements correctly, with a ruler and all that, right? You would get things that look like squares and cubes. So let's see. So here's an idea. Here's the first. 1, 2, 3, 4. Right? That should be over here. That. Okay? So in other words, this square over here, you see this square that I'm pointing out here? Gets slid along, it becomes this square, and that's a cube. Right? You see that cube? Right there? Okay, that's 1. Whoa. That cube is part of the hypercube, of the interior of the hypercube. That's nuts! But it is part of the interior of the hypercube, right? Okay, so we do this again. So now we take another cube. So let's see. Here we are. So we'll take this one here. Okay, see this one? Imagine it. Let me do. Now, I'm sliding it along here. So what do I see? I see this. This line goes over here. That's this line gets slid along here. This one here is here. This one, 1, 2, 3. There it is. Over here. That's this one. That's a square. And then finally, this one. Okay? What's left? What's left is, notice what you get. 1, 2, 3, 4, 5, 6, 7, 8. An octagon. In fact, if you look at a hypercube the right way, you'll get an octagon. It'll look like an octagon. It has to prove that mathematically. Okay, where are we? So what's left? These two. So this one, and then they connect to
the far right.
Down here. This one. And that should be this one. Oh, maybe not. No, that doesn't look right. Is it? Yeah, I think that's okay.
Right.
And then this one. And then this one. I think I got them all.
Ew.
I'm missing one? Yeah, I'm missing one. Yeah, this one. Okay? Alright, now, this sucker is a hypercube. It doesn't make any sense to you, right? But it is a hypercube because we've done everything the way we're supposed to do. We take each vertex, we slide it along the new imaginary axis, and you get this strange-looking creature, of course, that doesn't make sense in your head because it doesn't really exist except as a projection on a blackboard, right? But mathematically, it really exists, and these points, these vertices of the hypercube, are actually extensions of the notion of the vertices of a 3-cube. So the vertices of a hypercube would be 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, and so on. You write them all down, you get 16. This is great. So a hypercube is 16 vertices. A cube is 8. It has to have 16 because we took the whole cube and we split it along an additional dimension. So 8 plus 8, 16. Right? And this is all connected to binary numbers and all sorts of stuff in computer science as well. Right? Hypercubes in computer science also show up. Now, how many cubes are contained in this? Now, here's a good question for you. How many cubes do you see in there? This is going to be interesting. You think there's 8? Well, it's going to be hard to see, right? Yeah, how many? Huh? Infinite number of cubes? No. Yeah, not quite. I mean, it's a good guess, but... But you have to keep doing it to get infinite number of cubes, right? Yeah, but wait, no. Think of it this way. Each face generates a cube, right? Because you're sliding each face into the fourth dimension. So as soon as you slide each face into the fourth dimension, you've generated a two-dimensional cube. That's part of the interior of the four-dimensional cube. How many faces are in a cube? 6. Therefore, there's 6 cubes in a hypercube. Nuts! How can a hypercube be made up of 6 cubes? It's crazy, right? You can't imagine it. Big deal. So we can't imagine it. Mathematically, we can play with it all we want, and we get a nice structure to hypercubes. And then we can pull the same stunt in 5 dimensions. Of course, 5 dimensions is going to become really hard to sketch, right? There's lines all over the place. But it's the same idea. A 5-dimensional hypercube then consists of 4-dimensional hypercubes slid along this imaginary axis. The 16 vertices become 32, which is 2 to the 5th, right? And so on and so forth. This way you can construct infinite dimensional hypercubes. Do we worry about it? No. Don't worry about it. Okay? So that's pretty much what they look like. I may have forgotten the vertex, but no, it looks good. You can actually make out some of the cubes, right? Here's one of the cubes right here. This one. There's one.
I have a feeling for the next couple of calculus passages that should be like exploding my mind.
No, not this one. This one.
The last semester was like really good. Like last
See, that's a cube, but I just sketched it, right? That's one of the cubes inside the hypercube. Isn't that crazy?